This is lesson 13, calorimetry. So, what is temperature? You know, we go our whole life taking our temperature when we're sick or saying, what's the temperature outside? But do we really know what it means? Well, temperature is something very different than heat. Temperature is actually the average kinetic energy, or the average speed of the molecules in a system. So when you take your temperature under your tongue, you're actually measuring how fast the molecules in your mouth are moving. Heat, however, is not the same thing as temperature. So like we said, temperature is the measure of the average kinetic energy of the particles, but heat is the change in energy. So in order to have heat, you have to have a change in temperature or change in energy. So depending on the mass of the object and the amount of heat added and the nature of the substance, the temperature will change when an object is heated. So the bigger the object, right, the harder it is to increase the temperature. Or if you don't add a lot of heat, the temperature won't increase very much. And then the nature of the substance we'll get into more in more detail in a second. So to find the change in heat of a substance, we are going to use the following formula. So remember, heat is Q. So Q is going to be equal to the mass of the substance times the specific heat capacity of the substance times the change in temperature of the substance. So this CS, the specific heat capacity of the substance, is the heat needed to increase the temperature of 1 gram of material by 1 Kelvin, or 1 degree Celsius. For example, water has a specific heat capacity of 4.184 joules. So there is 4.184 joules required to raise the gram of water 1 Kelvin. So there's lots of different heats of reaction. For example, there's heats of combustion, which would be the heat that is generated or needed when 1 mole of a substance is burned in excess oxygen. There's other things like heat of formation, etc. They're all pretty similar. And in order to do these problems, there's a few rules that we need to follow. So the first is that enthalpy is an extensive property, meaning that the change in enthalpy is going to be proportional to how much reactant that you have. So here's an example. We have methane being combusted to form CO2 plus water, and this equation is balanced. Okay, and when this happens, the delta H, or the change in enthalpy, is 890 kilojoules, and it's exothermic, so it's negative. Now, this is for 1 mole of methane, because the coefficient here is 1. So to burn 1 mole of methane, you release negative 890 kilojoules of heat, or enthalpy. If you were to do 2 moles of methane, you're going to double the amount of heat that you release. And so you're going to multiply 2 by negative 890. So you're actually going to release, and this should be negative 1,780 kilojoules of heat. The second rule is that the enthalpy change for a reaction is equal in magnitude but opposite in sign to the delta H for the reverse reaction. So here's an example. We have methane from before being combusted in oxygen, and remember we said that the delta H for this reaction is negative 890 kilojoules. Well, what happens if we flip this reaction? So now, instead of the methane being combusted, we flipped it. So now we have carbon dioxide plus water going to methane plus oxygen. And you can see what happens to the sign of delta H. The sign of delta H is flipped. So before, when you combust it, you released 890 calories. When you take the products of combustion and combine them to make the methane and oxygen, you are going to have to add 890 kilojoules. And the third rule is that the enthalpy change for a reaction depends on the states of the reactants and products. And by states, we mean solid, liquids, or gases. So for example, gases and liquids do not have the same enthalpy. And here's why. If you have liquid water, don't you have to add heat to it in order to turn it to a gas? Yeah, you do. So This equation, 2 water liquid molecules going to 2 gaseous molecules of water, has an enthalpy change of 88 kilojoules. If they were the same, the change would be 0. So, in order to measure heat flow, we perform something known as calorimetry. And a calorimeter is a device that's used to measure heat flow. So this would be to measure the change in enthalpy in a reaction. Now remember, specific heat is the amount of energy required to raise the temperature of 1 gram of substance 1 degree Celsius, which is the same thing as 1 Kelvin. And we can find the specific heat experimentally. So to find C, if we're solving for C in our Q equals MC delta T equation, C would be equal to Q over M times delta T. So the specific heat is going to be equal to the quantity of heat transferred, Q, over the grams of substance, the mass, times the change in temperature. Here's an example. 209 joules is required to increase the temperature of 50 grams of water by 1 Kelvin. What is the specific heat? Well, we know that the Q is going to be equal to 209 joules. And we know that the mass is 50 grams of water, and the temperature change is 1 Kelvin. So when we plug this in, we get a specific heat for water of 4.18 joules per gram Kelvin, or 4.18 joules per gram degree Celsius. And if you remember back, we said that the specific heat of water is 4.184, so this answer is correct. And if we look down here, here's just some specific heat capacities of common substances. And if you look, water actually has a very high specific heat capacity. So what does that have to do with anything? Well, because water takes more energy to heat up and more energy needs to be lost in order to cool down, it actually affects our climate a lot. So if we look in the summertime, okay, this is you in this little lighthouse, okay, and the water actually takes a lot of heat in order to raise the temperature by 1 degree. And so what happens is the air above water is actually cooler because the water stays cool for a very long time because it takes so much energy to heat it up. And so that cools the air above it through conduction and convection, which means that this cool air is going to come onto land, and that creates a nice breeze. So if you live in this little lighthouse in the summer, you're actually going to get a cooler breeze coming in from the water. Well, then this air warms up over here because air actually and land have a lower heat capacity, so they don't take as much energy in order to warm up. And this warm air sets up a convection current where it returns back out to sea. It's cooled down because remember the water is still warming up. It takes a lot of energy, 4.184 joules for every gram of water, to go up just 1 degree Celsius, and it creates this convection cycle. Now, what happens in the wintertime? Well, again, our water is going to have to lose a lot of energy in order to cool 1 gram of water 1 degree Celsius. So the water actually stays longer or warmer longer because it has to lose a lot more energy in order to change the temperature just 1 degree Celsius. So the air above the water actually becomes warmer because it's in contact with the water here. And so this warm air actually comes out of the sea. It's cooled over here because remember the land over here cools a lot faster because it has a lower specific heat capacity, and then this breeze actually comes back out to the water, setting up this convection current. So if you live near the water, you actually have cooler summers and warmer winters than most people. It's more of a temperate climate. So how do we perform these calorimetry experiments? How do we determine the delta H, or the enthalpy change for a reaction? Well, what we do is we use constant pressure calorimetry. And constant pressure calorimetry uses a coffee cup calorimeter. So it's just a simple coffee cup. And because a coffee cup is not completely sealed, the pressure basically remains constant because the pressure in the room doesn't really change that much throughout the course of an experiment. So a coffee cup calorimeter has this coffee cup with an insulated lid, and you stick a thermometer in it. It has some type of stirring mechanism, and it also has, it's actually made of 2 coffee cups just to increase the insulation. So what you're going to do in coffee cup calorimetry is you're going to add your two solutions to the coffee cup, your reactants, and those chemicals that are inside the solution. So remember, solution is usually made of water and then chemicals inside the solution. The chemicals are actually the system, and the water that's surrounding the chemicals are the surroundings. So that's kind of a difficult concept for people to grasp. Any heat that is generated or absorbed by the system, by the chemicals, will change the temperature of the water. So if the chemicals release heat, the temperature of the water will go up. And if the chemicals absorb heat, the temperature of the water will go down. So what you're going to do is you're going to measure the change in temperature of the water from the starting before you combine the chemicals to the finish after the reaction is complete. And the change in temperature of the water is due to any heat being transferred from the reaction to the water. So if it's exothermic, the reaction is going to release energy to the water, or if it's endothermic, from the water to the reactants. So if we have an exothermic reaction occurring in here where the chemicals are losing heat to the surroundings, the water temperature will go up. So the heat that is gained or lost by the solution is going to be opposite the heat gained or lost by the reaction. So here, the Q of the solution is the Q of the water. So if the heat of the water goes up, that means that the reaction must have lost that heat, so it's going to go down. So what you would do is you would find Q for the solution, so you'd find Q equals MC delta T for the solution, and whatever the inverse of that, the negative of that is, that would be the Q of the reaction. So here's an example. When a student mixes 50 milliliters of 1 molar hydrochloric acid and 50 milliliters of 1 molar sodium hydroxide in a coffee cup calorimeter, the temperature of the resulting solution increases from 21 to 27.5 degrees Celsius. Calculate the enthalpy change for the reaction in kilojoules per mole of HCl, assuming that the calorimeter loses only a negligible quantity of heat, that the total volume of the solution is 100 milliliters, that its density is 1 gram per milliliter, and its specific heat is 4.18 joules per gram Kelvin. So here's the important data. The first thing that we notice is that the student is mixing 50 milliliters of 1 molar HCl and 50 milliliters of 1 molar NaOH. And so we know we're going to use our formula Q equals MC delta T. And if we write a balanced equation for this reaction, it is a double replacement reaction. And we know that the mass is going to be the mass of the HCl plus the mass of the NaOH. So because they tell us the density is 1 gram per milliliter, and we know we have 100 milliliters, that gives us a mass of 100 grams. They give us the specific heat of 4.18 joules per gram Kelvin, and our change in temperature is going to be 27.5 minus 21. So our temperature went up, meaning that the reactants must have lost energy. So this is exothermic. And when we put these numbers in for Q, we get a Q of 2,717 joules. Now the question is asking us for the Q, or the delta H, in kilojoules per mole. So this is how much energy the water gained, which means that, remember, the reaction must have lost that heat. So the reaction actually lost negative 2,717 joules, and if we convert this to kilojoules, we get negative 2.717 kilojoules, because remember, there's 1,000 joules in a kilojoule, so you have to divide by 1,000. Now, the question is asking us for the enthalpy change in kilojoules per mole of HCl. So we need to figure out how many moles of HCl we had. So we know that if we had 0.05 liters, because remember you have to convert milliliters to liters, and we know that there was 1 mole per liter because the molarity was 1, we know that we had 0.05 moles of HCl. So we take our Q and we divide it by the moles, so kilojoules per mole, and we're going to get a delta H value of 54.34 kilojoules per mole, and that's negative because it was exothermic reaction, remember. In an endothermic reaction, in a coffee cup calorimeter, the heat is actually going to be gained by the chemicals and lost by the surrounding water. And so what you're going to see is that the temperature is actually going to go down because the water is losing heat. Now, the major problem with calorimetry is that heat is always lost to the environment because you can never create a perfectly insulated system with a coffee cup. But for the most part, as long as you're careful, you can get a fairly accurate range for your enthalpy changes for really any reaction that we're going to do in the lab. Now, another type of calorimetry is called bomb calorimetry, and in this type of calorimetry, the volume is what is staying constant. And bomb calorimetry is really just used to study combustion reactions because the bomb can withstand really high pressure. So you can measure the enthalpy change inside of this bomb calorimeter because even though you're basically doing an explosion, nothing will happen to the bomb. So to calculate the heat of combustion in a bomb calorimeter, you have to know the heat capacity of the calorimeter. So unlike regular calorimetry, bomb calorimetry, to find Q, you're just going to take the negative heat capacity of the calorimeter times the change in temperature. And bomb calorimetry is much more precise than coffee cup calorimetry because the calorimeter is much more isolated. So here's an example of a bomb calorimetry problem. The combustion of methyl hydrazine, a liquid rocket fuel, produces nitrogen, carbon dioxide, and water. So you can see why you would not be able to do this in a coffee cup. Okay, so here's the reaction. When 4 grams of methyl hydrazine is combusted in a bomb calorimeter, the temperature of the calorimeter increases from 25 degrees Celsius to 39.5 degrees Celsius. In a separate experiment, the heat capacity of the calorimeter is measured to be 7.794 kilojoules per degree Celsius. Calculate the heat of reaction for the combustion of a mole of methyl hydrazine. So here's our formula for bomb calorimetry. So all we need to do to find Q is to plug in the heat capacity of the calorimeter times the change in temperature, so 39.5 minus 25 degrees Celsius. And that will give us a Q of negative 113 kilojoules. Now they want this per mole, so we need to change 4 grams of methyl hydrazine into moles of methyl hydrazine. So we're going to divide by the molar mass, which is 46.1 grams, and so we get 0.0868 moles. And so now we need to just take kilojoules and divide it by moles to find kilojoules per mole. So negative 113 kilojoules divided by 0.0868 moles gives us a Q, or a heat of reaction, of 1.3 times 10 to the third kilojoules per mole.